Welcome to a new video in my home automation series. And last time when I started this project where I installed this 16 channel current meter, which uses Modbus. So I built a custom ESP project to turn this Modbus information into MQTT messages, which then I put onto my Node-RED server while I read the data in the Node-RED server, and then push everything into InfluxDB so I can have a nice Grafana just like you can see here. And that's where we ended up in the last video. And now the first thing that I wanted to do is I wanted to create a very simple, well, maybe not that simple logic, which is going to look at these readings and can tell whether certain devices have been turned on or turned off. So the first thing that I wanted to tackle is that in my pantry I have a coffee machine and I also have a kettle. And so they are on the same circuit, so the consumption on those of those devices appear on the same, let's say, data source or data stream. So I want to see if I can build a logic which can say, okay, what is the state when these devices are not working, and when is the time when either the kettle or the coffee machine is turned on, and when is the time when they are turned off. It is somewhat similar to the automation that I did on my washing machine, which can tell me when the washing cycle is ended. But I thought it's going to be a little bit more complicated because, again, if I'm not monitoring a particular device, but I'm not monitoring any entire circuit, in this circuit breaker panel. So the, like the idle power might not be zero. There could be some other stuff connected to it. So I wanted the code to be a little bit flexible with, like, small consumer. Let's say that you have some devices in the kitchen that you want to monitor, but on the other hand, there are some phone chargers or, like, small displays or small lamps are connected into it. So how the code is going to deal with that and sort of like ignore those and then focus on these particular devices that we want to control. Of course, it all depends on the consumption of this device. And in my case, either the coffee machine or the kettle consumes a lot more energy than anything else, which is sort of like consuming a base load current. And also I was quite happy because these two devices are, again, quite different from each other. So the kettle draws around 9.8 amps and the coffee machine is around 6.5 amps or something like that. So that's the one thing I monitored, and as you can see on the in the graph here, it is it's fairly good. So you can see that it says here that the kettle got turned on, and then it got turned off after 3 minutes. The coffee machine was turned on and turned off, and also the dishwasher started. And that's where the code is not working perfectly yet, because you can see that it says that the dishwasher turned on and off in a couple of times, but actually it was just one washing cycle. But the way the dishwasher works is that it really drops down the consumption when, let's say, it's between cycles. So probably I have to tweak that part of the code a little bit, but at least it's working for the other two. So in this video, I'm going to show you how I did this in Node-RED, and then how it looks. And if you want to do something similar, then you can just copy my code. The link is going to be, like, the download link is going to be in the video description as usual. So first of all, let me change views because I want to show you the data first. And so this is what I get out of InfluxDB and what I view in Grafana. So it's looking at the last 6 hours. And then in these 6 hours, we had some, action. So this was like the morning, and you can see that this is how a kettle looks like. I mean, I can just tell from the current reading, and that's how the coffee machine looks like. And you can see that the coffee machine is quite different, as in, like, it has probably the initial cycle when it heats up the water, and then the pump starts, then the consumption is quite low, but then it jumps up again. So it's a little bit up and down, but again, the whole time it takes to make a coffee. So this is not the grinding type of coffee machine. This is the one which comes in the small coffee. So not the Dolce, it's Dolce Gusto. It's not, what's the other one with George Clooney? I forget the name, Nescafe. So if it would be the grinding machine, I think the cycle is going to be longer, and we see a lot more variety in, like, you know, the grinding motor starts up and then the heater and the pump and everything. So, but still the logic can keep with this amount of information. If you see, I think I mentioned in the previous video that we get data points every 5 seconds. Okay, so if I go back to the last 6 hours, and then, so that was the heater, sorry, the kettle. So as I said, kettle is easy. I mean, this is ideal resistive load. And what else? We have some interesting lights here. That is interesting. This purple one is actually the, I think that's the fridge. Yeah, so I would be, I want to create a different set of logic for the fridge, which probably looks at longer time data and then tries to analyze, you know, either patterns or consumptions or averages for a certain period. But that's probably for another video. I haven't even started working on that. And if you look at the washing dishwasher, I mean, that's a difficult one because as you can see, it, you know, it starts up almost at 10 amps, 10.1. So I'm assuming that that's when the heater element starts, and then, you know, the heater element stops, and maybe that's the actual washing cycle when the pump is running. So that's about 1 amp, and then the heating element starts again, and then again, and it drops. And I think there are some periods here. For example, we can see that there are periods where actually there is zero consumption. So yeah, 0. So maybe the machine is waiting between cycles. It's just, you know, waiting the water to, you know, drain to the bottom of the pan, and then it starts up again. So, you know, it's a lot more difficult to tell. But again, you can tell that there is definitely like the high points, which is usually in the beginning because it needs to heat up the water, and then you sort of like have to wait until the consumption settles to 0, probably, or a longer period of time than for a kettle or a coffee maker. So you can't just have one logic which is going to apply to all. But that's a good thing about, you know, collecting the data and looking at the data, because you can actually see, you know, how it looks like, and then you can change the code accordingly. So let's look at what we did, or what I did in Node-RED. And the entire flow is actually this much. So that's the complete flow, which I'm going to extract and make the link available in the video description for you to download. And the beginning, well, sorry, this much of the data is something that I already showed in a previous video. So we get the data from the current sensor, well, all the 16 channels, and then we convert the data into an influx dB line sentence. Is it called? Yeah, line sentence to ingest. And then I also have this node which shows me like when was the last update from the sensor. And that's pretty much it. So this only takes care about saving the data in the database, nothing else. And then that's the actual sort of like detection or event detection logic. So first is the data comes in from the current sensor, and this data contains all the 16 channels, as you can see, like all 16 channels. So what I do in this change node is in this particular one, I only care about the pantry socket, which is C04, so that's channel 04. So I put this into the payload, and I put the topic into data, because that's the data that we have or we need to look at. And I've also created an inject node which has a list of settings for the code to work with. And here I need to explain the entire logic. So the way I thought this is going to work is that the code needs to establish a baseline, which is not necessarily 0, but let's say baseline is a current consumption, which if I average over a set number of readings, in my case it's 10 readings, so I average the last 10 readings out, and I look at what the new reading that comes in. And then if that is within a baseline threshold, so let's say 100 milliamps in this case, then I treat it as, you know, still a baseline consumption. So these are the cases where you have a circuit and then you plug like a phone charger in, or the 4th charger is plugged in and you plug in your phone, so there is a little bit more consumption, but it's not like the amps or multiple amps that we want to look at in these particular cases. Again, if your device also consumes a very little power, I mean, like tens of or hundreds of milliamps, maybe this code is not going to work, but it works with the devices that I intend to use for the time being. So it looks at this baseline, and then it keeps looking at the readings, and it says, okay, this is still baseline because the change is very little, so that's our new baseline. And then another reading comes in which may be a little bit lower, again that's within the threshold, so that's within the baseline. And all of a sudden, when something like a coffee machine or kettle gets turned on, then the current consumption jumps quite significantly, and that's when we need to figure out what is the device that got turned on. Again, assuming that you don't turn on multiple devices at the same time, because well, this code cannot deal with that. But what I have done in these settings is you can define the devices that you want to look for. And as you can see, the logic is fairly simple. All we can do is we can define that, okay, we have a kettle on this circuit which consumes anywhere between 9.3 and 9.7 amps. That's sort of like the peak output. And we also have a coffee machine which is usually consumes something like 5.5 and 6.1 amps. So that's nice, and as we can see, the kettle sort of like consistently delivers that power consumption, but the coffee machine does not, because it sort of like jumps around. So the way the code works is that when we get out of this baseline, then that's the point where it tries to determine what the machine or the device is that got turned on. And then if we fall out of these brackets, but we are still not back at the baseline, so in my case, let's say the even on the washing machine, like the pump is still running, it still does a couple of things, so it still consumes more than what the usual baseline is, then it just says, okay, so this machine still must be working. It's not in that initial 9 or something 6 amps, but it's still not back to the baseline, so the machine still must be working. And that's the logic basically. And the way I implemented this in this function node is, oh, and by the way, if I haven't mentioned, so this settings comes in a topic as settings. So that's where this function node knows whether it's the data or the settings that it receives. Of course, it needs to receive the settings first in order to do anything with the data. So here you can see that we wait for, if we receive the settings, then we store it in the context. So in the context, you have, the settings, and you also have some data where all the internal calculation is stored. And if we don't have a settings, then it shows a message that we are missing the settings, so we can't really do anything. And then once we receive the data, then that's when we start storing this information. So the first thing that I did is that I create this current history, which, I mean, in this particular case is the last 3 readings. So I never look at the actual, the last data that has come in, but I average the last 3 readings. So in my case, I average the last 15 seconds of data. Again, assuming that whatever device that we want to look at runs for at least 15 seconds in that current bracket. So we average them out, we edit an array. If the array has more than 3 elements, then we just drop the latest one or the oldest one, and then we calculate the mean, so the average of these readings. And then that's when this baseline calculation kicks in. So we look at this average, and we also look at the average of the baseline, and if the difference between the two is less than the threshold, then we say that, okay, we are at the baseline. So then we do the baseline calculation. Again, that also does an average of the last 10 readings, just to make sure that we don't, any, bigger jump is not treated as an outlier. And so if we are at the baseline, we say, okay, we are at the baseline, there are no devices running, no device detected, and there is no selected device. And if we were not at the baseline, and we have a device selected, then we said, oh, we just returned to the baseline. So that device, whatever device that we had, must have been turned off. So it sends a message that the device has been turned off. So you can see topic off, and that's getting sent out on the second port of this function node. And then we calculate the baseline averages as well. And if we are not at the baseline and we don't have any devices selected, which means that this is probably the point and we just, the device just got started and the current consumption just jumped. So we need to find out what the device is. So then it goes through all this list of devices, which, I mean, I had two for one, you know, for the coffee machine and the kettle, and the other cases there is just one with the dishwasher. And then it just looks at whether the current, again, free reading average is within the min and a max. And if that's true, okay, then that's the device that we are looking for. And it sets the device name, and the device selected is true. So internally, it just notes it down that, oh, we have identified the device and the device is running. And if no device is found, then it just says, I am experiencing a current reading which doesn't fall into any of the brackets that we have defined. And then it just updates the status, which says, you know, we are at baseline, we have a device, we don't have a device, whatever. And as you can see on the first port, it just sends out updates. So this value is getting sent out. So you can use it for reporting, debugging, whatever. But what we actually care about is the second port, where it sends either the on or off messages that a device has been turned on or turned off. And that's what I get sent. That's what I use to send these messages. So here in the Telegram message, you can see that I created content with this plug type, and then the message.payload.activedevice.name. So in this case, that's like dishwasher or kettle or coffee machine, and it's turned, and the topic, that's on and off. And then in the brackets, I just show the baseline and the current, so the two main values. So you can see that the coffee machine got turned on, so the baseline is 0, and all of a sudden we have 5.87 amps, and that's within the, I think it was 5.5 and 6.1 for the coffee machine. And then when it gets turned off, you can see that the consumption drops. I mean, it doesn't drop exactly to 0, but it drops to, which is still within the baseline threshold of, I think, 100 milliamps. So that's nice, it's working. And then the kettle, I think you can see that it jumps up from 0 to 9.52 amps. So that says, okay, it's a kettle. And then it turns off, it actually goes back to 0, completely 0. So the code works, and it is able to see all these differences. So as I said for the dishwasher, because there is a slightly longer period in where it's not really doing anything, and I had at least assumed that even when it's not doing anything, that it still uses some, current, which is, let's say, more than, I don't know, maybe like 100 milliamps, because I think, I haven't really checked the specs, but I get readings for 2 decimal places. So let's say, 10 milliamps. So if something uses less than 10 milliamps, it just shows 0. So probably the internal circuitry of the dishwasher uses less than 100 milliamps when it's, just waiting in the cycle. So what I have done in the dishwasher is I increased these history averages or the current averages to 10 readings, because as we have seen sort of like here, that's too much. Let's look at another one. And dishwasher, so let's maybe look at this one. So you can see that I have 0, 0, 0, 0, 0, but if I average 10 readings out, there is a likelihood that I get some average which is going to be not much, but a little bit greater than 0. And I think for the for this dishwasher calculation settings, I configured the baseline to be 0.01. So again, I'm trying out with these different, couple of these different readings or values to see how I can fine tune the logic that it works with, these type of devices and those type of devices as well. And if that's going to be the fix for my issue, then probably I will move this number out into the settings so I can make the code perfectly same for both of these cases, because it's always a pain to maintain, two function codes which have the same logic. So if I need to change anything here, then I have to make sure that I copy it over to the other one as well. And that's why it makes sense to create subflows. And as you can see here, I have already started creating the subflows. And they basically, this is just a subflow of that single function node. The problem with this is that when you create a subflows, you don't see the context nodes. So like the way I can, see the data and I can just verify how it works. If you have a subflow, you don't see that. And that's probably something that might be fixed in a further, Node-RED update, but it's not working at the moment. And, for these initial phases when I'm debugging and I'm constantly fixing issues, I want to see these context nodes. So I think for the time being, I would use 2 individual function nodes, but probably at some point I would just create a subflow and change these to the subflows, because as you can see, they are identical. So, and of course they should work the same way. And to be honest, that's pretty much it. So that's how the code works at the moment. And if you want to implement the same, you can take this part, and of course your source can be different. You just need a steady stream of values. I mean, ideally these would be current values, but if it's like short-term consumptions as well, the code will work with these, because it doesn't really look at units, it just deals with numbers. And of course, at the end, I send Telegram messages to me, but you might change this one to, let's say, an email or some other means of notification that, suits your setup. So if you are interested in this, there is going to be a link in the video description. If you want to see the initial setup, I'm pretty much sure that it's going to be in one of the cards for this video. But I think that will be all for today. Thanks for watching, and hopefully see you in the next one.